Okay, welcome to Chem 121 here at SUNY Broome Community College. This is Dr. Daniel Brennan here for the Forensic Science lecture. Our first unit will be Safety in the Scientific Method, and then we'll follow up with other units until we're complete with the course. So I look forward to working with you this semester, and I hope you enjoy these video lectures. Okay, so our first topic for the semester is safety, and I can't think of a more important topic to begin the course. Safety is very important in the natural sciences because this is a chemistry course specifically, but chemistry, biology, geology, physics, so on and so forth. We tend to study matter and energy, and at least in chemistry in particular, we tend to deal with chemicals. Sometimes those are hazardous chemicals, so we do need to have safety in the forefront at all times. Now, this is an online course with online labs, but it's still good for you to have a knowledge of real-world lab practice because some of you may be going into the real-world lab at some point, and it's important for everyone to get an idea of how science really happens in the real world. As I mentioned, this is a computer-based course, right? So there's even special safety considerations for us in the online environment. So things like posture-related injuries, if you don't have a proper chair and you're not sitting upright and all those things. There's eye strain, there's muscle or joint injuries. You can get carpal tunnel syndrome, for instance, by not properly using your keyboard and mouse and those sorts of things. So I even included a link rather for some suggestions. It happens to be an Australian website, but there's other options out there if you prefer to do a search for this, but just so that you can think about things with your online course. Some of you may be working on laptops, some may even be trying to use smartphones. All these things are small and they weren't designed for long-term use, right? So hopefully you're working at a desktop watching these video lectures on a large screen, but if you're not, then you need to take even more frequent breaks. You need to be even more concerned with your online safety. All right, so again, we have the online labs, and there's some flexibility there as to when you actually complete those labs, as long as they're done in advance of the due date. But if this were a face-to-face lab, if you do go on to courses where you do have a lab component, remember, being on time to lab is important. It's important for a number of reasons. So not just the fact that you're professional and that you're on time, but we have personal safety and we have the safety of those around you to worry about in the physical setting. So you've got to be on time so that you don't rush, right? If you're late, you can't just rely on your partner, or maybe even you're working alone. You can't know that you have sufficient time to complete the exercise. If you're, more than a few minutes late, or even a few minutes late might be too much. And like I tell my students in the in-person labs, you won't be allowed in the lab outside the normal meeting time. So you need to complete the exercise in the allotted time, which means you need to be there at the beginning. So this is, again, for those who are in only online labs for now. This could be an issue in later experiences, but it's always important and professional to be timely. It's especially important in the lab setting because of the additional safety concerns. All right, another important consideration is eye protection. Your eyes are very important, and we want to make sure that they're working just as well when you're done with a lab as when you started. I mentioned eye strain specifically on that first slide because in the computer-based labs, there are some that go on for quite a while, and you need to take frequent breaks and make sure that your eyes are getting the rest that they need. In the physical lab, it's important to protect those eyes against any number of chemical agents and other concerns, physical implements that might otherwise injure those. So if you're doing a face-to-face lab, then safety glasses, safety goggles are an important part of that. I wouldn't mind if you're sitting there doing your online labs with some safety goggles on, as long as you're able to see well and there's no glare, but that's not required for the online, but definitely for face-to-face. The use of safety goggles is a critical and important safety guideline. In particular, if you happen to be working in New York State law requires that eye protection is worn in lab areas at all times, that the lab area is an active lab. So students in New York State colleges and universities are not permitted to wear hard or soft contact lenses in lab areas because they need to make sure that their eyes can be doused with eye wash water if necessary. And for the same reason, the visitor safety glasses aren't allowed for lab use for those populations because they don't provide sufficient safety for college level laboratory work. So just something to keep in mind, especially as I mentioned, for those who are going on in forensics, will be going on in the natural sciences, and will inevitably be taking some face-to-face lab experiences if you haven't already. So New York State in particular is very specific about safety eyewear in the lab setting. In addition to protecting your eyes, it's also important that you protect your skin. So appropriate protective clothing is the first line of defense against chemical irritants and corrosive chemicals that might damage skin. So appropriate protective clothing should be worn at all times in the laboratory, just like the eye glasses or eye goggles we mentioned previously. Some examples there: shorts, short skirts, sleeveless shirts, or sandals are not permitted in the physical lab. For this course, if you're doing an online lab, you're welcome to do that in your shorts, but if you're coming to campus to do a campus-based physical face-to-face lab in the natural sciences, then that's not probably going to be permitted. What do we encourage? Well, long pants, shirts that cover your midriff, closed-toed shoes, those are all required. And that's to protect the skin, right? The skin that many of you like to show off in the summertime. We want to make sure that that's protected against chemical irritation, chemical burns. In case you have those areas exposed in the lab, then you won't be able to expose them later on when you might choose to. All right. It's even wise to wear a lab coat or a lab apron just to offer that extra level of protection if you're in a face-to-face lab in the natural sciences. So we're protecting our eyes, we're protecting our skin. We also want to limit any intake of chemicals into our body through our mouths. So eating, drinking, smoking, those are all prohibitive behaviors in laboratories because they could provide a route of entry for chemical substances to enter the body. So you should never bring food or drink into lab areas. You should always make sure that you've had something to eat and drink before lab, and then wash your hands after lab and go and have something else if you need to. But during lab is not the time, at least not in the laboratory itself, to be consuming food or drink. Unfortunately, a lot of these safety rules happen because of accidents. In particular, sometimes groups were collecting chemical waste in soda cans, and then a student might unsuspectingly drink out of that can, and there could be any number of toxic substances there. So we don't want to put our mouths on anything in the laboratory, so that's why we never eat, drink, or smoke in physical laboratory settings. If you choose to have long or loose hair, it should be tied back in the laboratory setting. So it's your responsibility to tie back your hair. Don't expect your instructor to necessarily provide you with rubber bands or anything like that. If you're in a face-to-face lab and you do have hair that's longer, make sure you bring your own implement to keep that hair back and out of the way, particularly if you're working with a heat source or open flames. Those open flames are a big danger with long, loose hair, especially if any styling products are used. A lot of those hair sprays and hair gels are alcohol-based, and that's flammable. And then if that happens to contact the open flame, then it can result in the very least, this unpleasant smell of burning hair, and at worst, certainly a very serious hair fire. So this is another important safety rule that for our online labs, you're welcome to have your long or loose hair however you like it, but in the physical setting, we would certainly expect that your long or loose hair would be tied back. Now, a lot of the chemicals that might be used in a face-to-face forensics or other chemistry lab could pose a risk to anybody, but they certainly pose a special health hazard to pregnant women or people with other health problems, people with chemical sensitivities or breathing disorders, or any number of other issues that we might consider. So if you're in that special population, make sure you do tell your lab instructor if you do take a physical lab that you have those concerns, and that way they can help advise you, right? So the science lab instructors, even if they're doctors, right? Usually it's a PhD doctor that would be in a science lab, and we may not know an awful lot about health. We have a doctorate in our field because we've contributed to an increase in knowledge in that field. So I happen to have my doctorate in chemistry because I did significant research in that field, but none of it concerned human health. So you'd certainly want to also discuss your health status with your personal healthcare provider and maybe show him or her the sorts of labs you'll be completing, the chemicals you'll be using, that sort of thing to get the proper medical advice. But as I said, certainly tell your lab instructor as well so that they can advise you on how best to proceed if you happen to take a face-to-face lab in the natural sciences. Another common issue is that people just treat the lab too casually, right? You're used to being able to sit anywhere you want in a classroom, so you think that the laboratory is the same sort of situation where you can just, have a seat, set your things down, and that's not a good idea in the lab setting. So we don't ever sit on the desktops. We don't even put our backpacks or other things on the desktop themselves. There's usually a special cubby area where you might be able to put your coat and bag and things like that. And that's because we are always concerned about contamination, right? We don't know what's on there. We don't know that it's been cleaned appropriately. We're not sure what chemicals were used previously. And I mentioned that some of the things we use can cause problems for people with sensitivities. Some are just plain hazardous and will cause problems for anybody. If you happen to think that, that puddle of liquid on the bench top is water, you might be right and you might be wrong. So if it's a strong acid or base solution, that could be quite dangerous to sit in or to have your bag in or anything like that. So don't make assumptions in the laboratory. And if you're going to assume anything, assume the worst. Assume that everything is, a dangerous substance that's contaminated the workspace, and let your instructor know accordingly. There's a lot of trust that goes into a physical face-to-face lab setting, and the instructor and the students in those labs have to count on each other to be seeking the most optimal conditions for everyone. In this instance, we're talking about air quality, so you want to make sure that you're providing the best possible air quality by doing your work in the fume hoods when necessary. If you're dealing with volatile substances, if you notice there's a problem, an airflow indicator sounds, or things just don't seem to be working right over there, make sure to let your instructor know. Don't take it upon yourself to silence any alarms or to just figure things must be fine, because sometimes they're not, and your instructor might need to give you specific instructions. So don't expect someone else to take care of it. If you notice a problem, then go to the instructor and make sure he or she's aware of it so that it can be appropriately acted upon, because maybe it's nothing, maybe it's something. It's usually not in the purview of the student to make that call. That's why we'd always approach an instructor if there's any concern, especially as concerns air quality around volatile materials. Now, you ordinarily wouldn't just show up to a lab and expect to be clued in on everything. There's an expectation that you're prepared in advance, so you have an idea about what you're going to be doing that day. You're there on time. You're waiting for the instructor to be present before you begin. He or she's likely to have some important instructions and safety announcements and environmental concerns and how to deal with hazardous waste, those sorts of announcements to make. You would certainly be curious. That's why you're in a science class in the first place, but you would not conduct your own unauthorized experiments. You might ask your instructor about what would happen if we mixed A and B instead of the A and C that the experimental procedure calls for, but you would never take it upon yourself to do that without asking permission first. You'll also want to read all the labels carefully, because sometimes a reagent might be the same reagent in different concentrations for different parts of a laboratory exercise. So 1 molar is a lot different than 0.1 molar or 0.001 molar, so on and so forth. Out of courtesy to your colleagues in the lab, you wouldn't remove reagents from work areas. They're probably going to need them, and oftentimes if a reagent's in the fume hood, it's because it either has an unpleasant or odor, or it's a dangerous substance. So you wouldn't want to take those out unless you've been instructed to do so. And finally, you don't want to contaminate reagents. You don't want to be, putting a little of A into a little of B in the stock bottles that the other students will be using, because that's going to have consequences for yourself and for later students if you've contaminated those reagents. We always want to pour from the reagent bottle into a secondary container and then take from the secondary container to minimize contamination issues. All right, so it sounds like there's a lot of responsibility for these face-to-face labs, and that's because there is. So another responsibility that students have in those settings is to check the equipment and the glassware that they'll be using. So you always want to inspect that equipment and glassware because the instructor probably has tried to do a job of that, but it's sometimes difficult, and there might be labs within 10 minutes of each other, and there's just not time to check every single piece of glassware or piece of equipment in between labs. So you'll want to make sure that the electrical cords are in good condition. There's no fraying or loose wires or things like that. You want to make sure that the glassware is in good shape. It's free from cracks. Sometimes these tiny star-like cracks that can be difficult to see. If you look carefully and you notice those could be a warning sign that something far worse is going to happen. So if you notice any visible stars or cracks in the glassware, you want to let your instructor know and see if he or she will replace that with a fresh piece of glassware before any further breakage occurs. We also never want to handle electrical equipment or glassware with wet hands, right? If you know anything about electricity, you probably know it does not work well around water, so you don't want to be putting wet hands near the plugs of electrical equipment. And glassware can be far more slippery with wet hands than with dry hands, so you just want to be careful. Hand washing is great, we'll talk about that, but you want to make sure that your hands are dried thoroughly before you go to handle electrical equipment or glassware. Because you do not want wet hands for those particular types of equipment. Hopefully we've got a lot of people like me who try to stretch their dollars and never waste. Well, this is one time where you actually will save money by wasting things. So what do I mean by that? Well, if you have excess materials or if you have chemical waste, you want to make sure that you take care of that appropriately. Don't put it back into the reagent bottle, because now you've contaminated a whole bottle instead of disposing of just a little bit of material. So it seems counterintuitive to those who don't want to waste any drops of anything, but it's actually far better to dispose of excess chemicals or chemical waste appropriately than to try to save money by doing things inappropriately. So if you're dealing with organic solvents, there's likely going to be waste containers there, and there's usually at least two different types of organic solvents you might use, halogenated or non-halogenated, and you would want to make sure that you put them in the appropriate waste container. Glass, if you break any glassware in a physical lab, you want to make sure you put it in a glass disposal box so that the custodial staff isn't injured by broken glass just placed in the regular garbage. Aqueous waste can sometimes be safely flushed down the drain. Other times it may need a special container, like a heavy metal waste container or a silver waste container is often used for aqueous waste containing silver ion. So that's why you want to make sure that you listen to your instructor and that you dispose of the waste appropriately, because there are these different waste concerns for different types of chemical materials. If you were to injure yourself in the physical lab setting, it would be important to let your instructor know. Even if it seems like a minor injury, you want to let the instructor know, just because he or she has a better idea of what you're dealing with, and maybe if there's anything that you should be on the lookout for that they could advise you on. Certainly you could always go and see a health professional if you feel like something's not right with your body and you know that you were exposed through an accident or injury in lab earlier. then that would certainly be cause to at least go and get it checked out. Maybe it's nothing, maybe it's something. You know your body, you know when things are not quite right. So certainly that would always be an option if you were in a face-to-face lab and you did have an injury or an accident that allowed chemical exposure, a route of entry for a chemical agent to get into your bloodstream, for instance. So basic first aid reminders, these apply to the kitchen as well as to physical labs in the natural sciences. So if you burned yourself, you would want to cool that burn with cold water right away. If you're in a lab setting, notify the instructor. If you're at home in the kitchen, maybe let someone know if there's anyone else there. Otherwise, just cool with water for a good minute or two for a burn, just to make sure that you've really done enough time with that cold water to minimize any damage to the skin. If it's an acid or base spill, if you can get that area under the sink as well and rinse with cold water, that's the best thing for you. Notify the instructor. We'll talk about safety showers if it's a large scale spill in a physical lab, but hopefully it's a small spill over an area that you can easily get under the sink with cold water. So same first aid approach, whether it's a burn or a spill in this particular example. Speaking of those chemical spills, let's say it's a little larger spill than just splashing a drop or two on your hand that you get quickly under the sink and rinse with cold water. For any larger spill, you'd want to notify your instructor immediately. If it's an acid or a base, you'd want to neutralize it appropriately. Clean up the spill. If you're not sure how to clean up the spill, then consult your instructor for advice to make sure that the spill is appropriately neutralized and cleaned, so that it doesn't pose any future risk for anyone else in the lab. The next few slides will go through some standard safety equipment that should be in any physical lab that you might take. So we'll just talk about the different options. Obviously, if you were in a physical lab, you'd want to know the location of those safety features before you begin work in the lab in case there was an accident or an injury or the need to use any of those safety features. The first safety feature that's present in physical labs in the natural sciences and frankly in a lot of workplaces as well would be an eye wash. So an eye wash station is provided in case of an accident or injury to the eye. Exposure to chemical irritants, for instance, would be an instance that would warrant a trip to the eye wash. Strangely, people might expect they would want to aim that eye water right at the eye. Actually, you want to aim it at the base of the nose, and so that it'll flow up through the eye and rinse the eye free of chemicals rather than just going right for the eye itself and maybe missing that. You want it to go up from the base, the bottom part of the eye, and flush through to make sure that it rinses through the eyelashes and the eye itself. And it's not going to be a quick thing, right? It's going to take 15 minutes. That's our minimum advice for flooding the eye with water to remove those chemical irritants. If you have contact lenses in, then it's not even going to be possible after 15 minutes probably to remove those residues. But the 15 minutes should be a good amount of time while the ambulance is on its way to have you brought in for assessment by a healthcare professional. So that's why we strongly discourage the use of contact lenses in physical labs in the natural sciences, because the contact lens can hold that irritant to the eye, and the eye wash won't be sufficient to provide a rinsing of that irritant if it's trapped behind a contact lens. Another safety feature that would be present in a lab in the natural sciences would be a safety shower. So while the eye wash is effective for rinsing small amounts of chemical irritants from the eyes, the safety shower is going to be effective on large-scale spills of corrosive chemicals over much of the skin or clothing. And again, we're not talking about something that could easily be addressed by putting that area under the sink. We're talking about a very large scale spill of corrosive chemical that's on much of the body. It would be the same sort of idea as the safety eye wash in that you're going to be rinsing for a good 15 minutes to remove all of those residues. You'd also be removing the clothing that's going to hold those residues to your skin. Of course, it's an unpleasant thing, and we certainly would want to avoid it, but if necessary, the safety shower can be very important in preserving your skin and preventing chemical burns on the skin if it's done quickly and appropriately. It's also an effective method if there's a clothing fire or a hair fire. We talked about long or loose hair earlier, so the safety shower would very quickly put that out. We wouldn't need 15 minutes under there in those situations, but you would certainly want to use that if the safety shower is easier to get to, closer than the safety feature we'll talk about next, which is the fire blanket. Okay, so the fire blanket is a blanket that will smother the flames and will not burn itself. So this, as we just mentioned, would be useful in the event that there's a clothing or hair fire. Follow those stop, drop, and roll instructions you probably learned in elementary school, and that would be effective for putting out the clothing or hair fire. Again, if it's more convenient to use the safety shower, then that would be another option for this particular application. Okay, so speaking of fire, fires unfortunately do happen in the natural science labs on occasion. Hopefully never unintentional fires in the lab that you're in, but if that should occur, then there's likely a fire extinguisher there that would be appropriate for a laboratory fire. If you've had fire extinguisher training, then you might be someone who would be able to use that fire extinguisher. If you haven't had the training, then it's not worth trying to learn on the spot. Just sound the alarm, evacuate the building, let someone else in the lab who's had the training address it, or let the professional firefighters address it when they arrive. Okay, the final safety feature that's probably present in your physical face-to-face natural science lab is a first aid kit. The only problem is these usually have just minimal first aid supplies, maybe some burn gel, some band-aids, so they're not usually very well stocked, but if you do need some burn gel because you had a small burn or a small cut that requires a band-aid, then you should go ahead and see your instructor. Usually I don't encourage students to help themselves just because if the instructor's not monitoring the first aid kit, then he or she won't know when you're out of bandages or a burn gel or whatever. So that's why I always encourage students to go to the instructor just to ask, and then the instructor will probably walk you over and open it up and check to make sure that what you need is there, and be happy to give you what you need as long as it's nothing too elaborate, because as I said, there's usually not too much in these first aid kits. So once you've established that basic layout of the safety features in the lab, you'll also want to think about the emergency exit route if there's an emergency phone, or if you're expected to use your own cell phone as the emergency phone. So that would be an important safety feature as well, is to make sure that you're prepared for an emergency that requires you leave the lab. So your instructor is probably going to have a route that he or she identifies, because you're going to want to meet up outside the lab in a safe place away from the potential fire, right? Oftentimes it's just a fire drill, but sometimes it's the real deal, and you'll want to make sure that you meet up with your instructor so that he or she can take attendance, account for everybody, and then either dismiss. If it's a real fire, it's probably going to be a while before anyone can get back in the lab, or let you know how long to expect to wait as the drill concludes. So it's important that you know about that, so that if it does happen while you're in lab, then you'll know what to do. Some particular safety and environmental concerns will come up from time to time, especially in chemistry labs. So your instructor generally will stress those appropriate techniques for the particular safety or environmental concern at hand. There's also safety data sheets, SDSs as they're called, that you can consult for valuable information, and they make these for pretty much any substance, and often a lot of solutions that you might be working with. They have them for water, for air, for any particular chemical substance that you might be encountering, and they'll talk about the different safety concerns and how to dispose of it properly and things like that. So directions for appropriate waste disposal should be given to you by your instructor. If you either don't hear it or you're not sure that that was said, then definitely ask. You don't want to make assumptions. Even if you've consulted a safety data sheet and it happened to give information on that, you'd still want to check with your instructor, because he or she would be the best, most knowledgeable person about how to deal with that waste from that particular lab site. We'll address a few specific safety concerns now, and the first one we'll talk about is pipetting. Pipettes are used to deliver specific volumes of solutions to the reaction vessel, whatever that might be, a beaker, or whatever you're using for that lab. So you would never want to pipette a liquid directly by mouth. If you've used pipettes, or when you use them, if you're going on and haven't had a physical face-to-face lab just yet in the natural sciences, you'll see that pipetting itself takes some getting used to, and you'll even understand why it might be tempting to put your mouth on it, as we see in our picture. But certainly, for reasons we talked about several slides back, we never put our mouths on anything in the laboratory, and certainly we do not use our mouth to help pipette. There's either bulbs or pipetters that you'll use if you end up needing to do this pipetting technique in the physical setting. We'll have some online labs that will mention pipetting and have you click on things that would involve pipettes, but obviously it's a totally different thing to click a mouse than to actually pipette by hand and never by mouth. Now, in the natural sciences, we like to use our senses, but in the science lab, one sense we cannot use is the sense of taste. We never taste a solid or a solution in the lab, even if we know that it's salt, sodium chloride, something that would be fine to taste in the kitchen at home. Once we put it in the lab, I mentioned those secondary containers. If it wasn't a clean secondary container that salt's been poured into, then you're running the risk of consuming whatever contaminant was in there, and that could be a very dangerous mistake if you're not considering that there could be a significant contamination present. So we never taste a solid or a solution in the lab. Once it's in the lab, it's a lab chemical, and so the only exception might be if you took a kitchen chemistry lab, for instance, where there's no hazardous substances allowed and everything is intended to be consumed. But anything else, any lab that uses hazardous substances, we would never taste a solid or a solution. And if you're not sure if it's allowed or not, ask your instructor and he or she will be sure to let you know. All right, so the sense of taste is a no-no. The sense of smell we can use as long as we have appropriately wafted the chemical reagent. So we never forcefully sniff the chemicals directly. We use a wafting technique where the chemical source is a safe distance from our face, and we waft the vapor up with our hand to detect just small amounts of the substance without allowing large amounts of it to enter our nose. So that's how we might sometimes use the sense of smell to safely detect odor, but as we said before, the sense of taste is a no-no in the science laboratory. I've already mentioned contamination several times, and let me just remind you that reading labels can help prevent contamination by making sure that you have the appropriate substance in the appropriate concentration at the appropriate time. You never return unused chemicals to reagent bottles. Again, I'm as stingy as anybody, but even I know better than to put it back in there, because now you've ruined the whole bottle instead of just dealing with a little bit of excess as waste. Finally, we would never put our own pipette, dropper, spatula, whatever, into a reagent bottle. We always pour into a secondary container first, and that's what we would insert our pipette, dropper, spatula, etc. into, so that we're not contaminating the stock bottle. And if there is an issue, then we've only contaminated the small amount of reagent that we've poured into that secondary container. Now, in the physical lab setting, obviously there's going to be times where you'll pour reagents, and you'll want to keep those away from your face, right? Even if you're wearing your safety goggles, as you should, you want to avoid having any material spatter onto your face, especially the unprotected areas of your face that the goggles won't cover. You also want to make sure that you're in charge, right? Don't kneel down below the chemical and let it be in charge. Make sure that you know, hold it at eye level, pour appropriately and safely, so that if there is a spill, it's going to splash down at your feet and not go all over you and require a trip to the safety shower because you knelt down below pouring level. We would take special safety considerations when heating reagents, for instance, we never lean over the heat source because we don't want to allow our clothing or hair to catch fire. Always make sure someone's watching a hot plate or a Bunsen burner flame, if for no other reason than to allow other students to be aware that it's heating. Hot plates don't look any different, hot or cool, so if someone's always there near it, then you can warn the other students, you know, be careful, that's hot. Bunsen burner flames, you don't want anyone tipping it over, or if it goes out, you don't want the, you know, uncombusted gas to make an unpleasant odor in the room, those sorts of things. If you're heating a test tube in either a Bunsen burner flame or in a water bath on a hot plate, you want to aim those test tubes away from people, because if they suddenly spatter from rapid boiling, that could you know, that hot spatter could injure a student if the test tube is being pointed at a student instead of at a wall or someplace that the spatter would not cause injury. And finally, if you're handling glassware, you always want to be cautious. You want to always treat it as hot glassware because it looks the same, cool or hot. And if you're not sure if it's been in the heat source long enough to get hot, you just want to make sure that you're handling it as though it were hot, because it's not going to look different, hot versus cool. Okay, and so our final safety concern is hand washing. So wash your hands frequently. Wash your hands definitely before you leave the laboratory because you want to remove any of those chemical residues that might be on them. If you followed instruction and removed contact lenses before lab, then certainly you'll want to wash before you leave the lab and then wash again in the bathroom before you put your contacts in, just to be extra cautious about those chemical contaminants with a substance that's going to be going into your eye. So wash frequently, wash thoroughly, wash well, right? Our little graphic there tells us the entire washing procedure should take 40 to 60 seconds. It's not one of those 2-second rinses, right? It's a thorough hand washing because you've been in a science lab. You want to make sure you've removed any residues that could have irritating or unsafe chemicals. All right, so to wrap up the first topic from Unit 1 here, safety begins with you. So really, it's your responsibility to keep the lab a safe place for yourself and for others. This online lab, hopefully there's not any real safety concerns. A lot of the things we'll be doing virtually would be things that we'd be concerned about face to face, but obviously the virtual lab setting is a different story. But if you are in a face-to-face lab setting in the future, make sure that you know all you can know about safety in that laboratory. Make sure you exercise your responsibility for your own safety and the safety of your coworkers, and make sure that you practice safe chemistry because as we see in our little graphic, lab safety, it's no accident. Okay, so now we'll transition into our second and final topic for this first unit, and that is the scientific method. So science is a process, right? Science is a verb as much as a noun. And so if you want to do science, you generally will follow this basic method, although it's not always as stuffy as we make it sound, and we'll talk about that as we go on. But it's easier to present it as this process, even though sometimes the particular process has a slightly more free-flowing sort of, at least origin. So first, we tend to state the problem or pose a question. Then we'll gather information so that we can form a hypothesis, plan and perform an experiment to test that hypothesis, analyze the data from our experiment, and then finally draw conclusions. How did our hypothesis stand up? If it didn't do so well, we go right back into the experiment data end of things, as you see in our little graphic there. If the hypothesis withstood the test of time, then maybe we just want to duplicate our experiment, or others duplicate our experiment, and depending on how important it is, maybe it goes on from there. Okay, so looking at that first step, state the problem or pose a question. So Science demands a problem or a question, right? We're inquisitive people. We want to solve problems. We want to ask questions. And that's why we'll never run out of things to do, because there's always problems, there's always questions. And if you're a curious scientist, you'll always have work. So it has to be something that you can solve or test, right? So this is where, the religion and science have their divide, right? It's, the question of God. We can't solve that question because we can't really test that question. So science and religion are different spheres. It's not that science is versing religion in some all-out battle. It's that, it's not a sort of question that we can test. So that's not a question that we can pursue scientifically. If we're asking a question, the question can be simple, though, right? As long as it's testable, which we just said, we're not going to test that existence of God question, even though we all may wonder about it. But the question is as simple as, why is this like that, right? We can test that. If it's matter and energy, we can test it in the physical universe. If it's beyond matter and energy, we really can't test those questions or solve those problems. So we have our conducting polymers as an example. So the way conducting polymers were discovered, and unfortunately or fortunately, depending on your take, a lot of the major discoveries were by accident. So conducting polymers really were discovered by a graduate student using far too much catalyst for the experiment, and rather than just scrapping it, throwing it out, and denying that they wasted all that catalyst when their advisor came to question, they showed the product, and the advisor saw that this is a neat thing. And so it's why is this substance shiny when we wouldn't expect it to be shiny? That can be the question, and then pursuing a question like that can give rise to a Nobel Prize winning discovery like conducting polymers. So the conducting polymers weren't something that people were trying to make. They were just a discovery that was made possible by a student's mistake and scientists asking questions about why that mistake resulted in the product that it did. So once you've decided on your problem or your question that concerns matter and energy and is testable using the physical world, you try to gather as many observations and draw inferences from those observations to move further in your study of that particular question or problem. So just to be clear, an observation is learning something using one or more of the senses, right? So touch, taste, sight, smell, and sound. Using those senses to learn about the physical world is making an observation. And an inference is when an explanation is applied to that observation. So it's using the observation but giving some explanation to it. So inferences require much research from reliable sources. In the sciences, we tend to rely on the primary literature, which is scientific peer-reviewed journal articles. For our most part is the source that we might use for a high-level science project. If we're looking at something in the elementary, middle school, high school realm, then maybe an internet search could be an appropriate first step. But it's really that peer-reviewed scientific journal article that's the gold standard for researching information in the sciences. So the next step is to form a hypothesis. So a hypothesis is an educated statement that seeks to solve the problem or answer the question based on the information gathered. So it's a statement, it's not a question, right? We asked our question up front. Now we're looking to move further to have something testable, right? So hypotheses are often composed as if-then statements. So the if part would concern what's being tested, the then part would be the perceived outcome. And the example we give here from the text is if bacteria is exposed to increasing temperature, then those bacteria will die, right? That's the hypothesis. Maybe it happens, maybe it doesn't, right? There's certain, thermophilic bacteria that just love the heat. And there's a certain temperature at which even those will die, but you might see that before they die, they do start to increase with increasing temperature, and that would run counter to your hypothesis. So forming that hypothesis is really just using the research you've done so far to try to have some sort of expected result. It doesn't necessarily have to be correct, but it certainly is usually a logical statement that would typically be correct. It's when they're disproven that the things are most interesting with hypotheses. So after you've developed that hypothesis, you go on to the planning stage. So you'll plan the experiment, then perform the experiment to test that hypothesis. So when testing a hypothesis, your experiment will inevitably involve variables. So a variable is anything that can change throughout an experiment. And we think of experiments in a chemistry course probably as happening in a chemistry lab, but a lot of experiments nowadays are done on computers or with models or things like that. So we don't even have to limit ourselves to the natural sciences. We have other sciences, the social sciences like psychology, or the other types of sciences like in the business arena, they might do things with surveys and those sorts of experiments. So just realize that it goes beyond the natural sciences, and it certainly goes beyond the lab itself as you might think of it, especially based on the first topic where we talked a lot about a traditional science lab. So if we're looking for a controlled experiment, which is what we tend to want in the sciences, so that's the way that we can control for just one variable. So one variable is changed at a time, so then we know the impact of just that variable. If we start changing lots of things at once, then we won't know which of those changes had the greatest impact on our experiment. An independent variable is what's actually being tested, so that's the one in our previous example where we said that if we increase the temperature, then eventually we'll kill all those bacteria. Well, the temperature would be the independent variable because that's what's actually being tested. We would raise the temperature by controlling a heat source. The dependent variable has its outcome determined by that independent variable. So the dependent variable in that example would be the number of bacteria that are alive at a given temperature. So we start with a certain bacterial population, we increase the temperature, that's our independent variable. The dependent variable is now how many bacteria are alive at temperature X, Y, Z as the experiment progresses. So hopefully that gives a better definition of those variables and how we plan and perform that experiment based on the hypothesis. Now that we've conducted the experiment and acquired some data, we'll have the opportunity to analyze the data. So after the experiment's done, the results can be interpreted. So the data can be compiled into charts, graphs, diagrams, etc., so that we can more easily see those relationships. If you go on in the biological sciences, for instance, you'll see that oftentimes you take the natural log of something to compare. And so that's just a mathematical operation that helps to give a more meaningful relationship than if you just take the raw data. So that's, again, just something that's commonly done there for something like bacterial growth and decay, which is the example that we've been using. There's qualitative data and quantitative data. So qualitative data isn't measured with numbers. So qualitative data would be observational type data that might give you information about, say, a chemical used, but not necessarily the amount of the chemical. Quantitative data is numerical data that can be studied mathematically, and the quantitative data for our example would be the exact temperature that we used and the exact number of bacteria that are still alive at a given temperature in that sort of experiment. So quantitative data tends to be what scientists are after, but again, qualitative data can be important depending on the nature of the experiment and the nature of the question or problem that you're trying to solve. Okay, so the final step for our very formal dry sort of scientific method approach that we've been talking about would be to draw the conclusions. Again, it's sometimes a little freer form and more exciting than this, but for the most part we do follow a method because science, as I said before, is a process. So drawing conclusions typically is the last step. So after we've analyzed that data, we can assess the hypothesis, right? That if-then statement that we made. If it's unsupported, the data analysis shows that the hypothesis was incorrect or not supported by the data, then we can amend that hypothesis and we can plan a new experiment to try to get at what is actually happening with our problem or our question. If it is supported, then we should, again, a good scientist would repeat the experiment a few times to make sure that support is real and that we didn't just see something unusual that one time. And then we can share our results with the scientific community. That's an important part of science. That's the only way science moves forward, is by individual scientists sharing their results so that the scientific community can make progress. Finally, if it's confirmed and it's of fundamental importance, that hypothesis may become a theory. So oftentimes people will sort of dismiss theories, right? Oh, that's just a theory. Well, in science, a theory is pretty much the highest you can get in a given area. So atomic theory, for instance, is the whole basis of chemistry, that there's these tiny little things called atoms, and those atoms behave in predictable ways. And again, it's a theory because it's the broadest explanation for all of that evidence. There's also in our little graphic theory versus law. So sometimes people don't understand a scientific theory versus a law that makes it up. So for atomic theory, you might have the law of definite proportions, that chemical substances form in these simple ratios. So a law is typically a short mathematical statement in the physical sciences, whereas a theory is a much more overarching explanation as to why everything happens. So you'll typically have various laws in a given theory, like you'll have the laws of thermodynamics, for instance. Thermodynamics gives a theory of how substances behave with heat, and you have the specific laws that describe it. So that's just a short description of the theory versus law, which is a question that often comes up, especially with beginning students in the sciences. Now here in forensics, the forensic scientific method is a little different than the traditional scientific method we talked about. So here in the forensic setting, the event under study has already taken place. So whatever it might be, and again, it's not always a violent crime, but that's what tends to be what all of these crime dramas are about. Forensics applies to both criminal and civil law. So you could have, someone misrepresenting the amount of fat in ice cream would be a matter for forensic scientists to analyze the ice cream samples and see if there's really the amount of fat that's being reported, or if it's higher or lower than reported, and that sort of thing. So just keep that in mind. It applies to both the civil and the criminal acts. We just tend to focus on the criminal because they tend to be the more interesting types of activities to explore for the general public. That's why you have all those crime dramas and things like that. I don't think there's a whole lot of things about analyzing foods and going after the food companies that misrepresent the label. So working from the particular event, which will use as an example a murder. Someone's discovered to have been murdered with a 9mm weapon, for instance. So investigators will collect witness statements. If there's any witnesses available, we'll listen to them. Sometimes witnesses are credible, sometimes they aren't. And there'll also be a collection of physical evidence. There's always physical evidence, and physical evidence cannot be wrong, although it can be misinterpreted. So witnesses can be wrong, but physical evidence can never be wrong, but unfortunately its interpretation can be incorrect. So a hypothesis is formed regarding the suspects and who might have motive and that sort of thing. The forensic analysis of that physical evidence informs the hypothesis, and then the likely suspect would be prosecuted based on the district attorney or whoever's right it is to bring that prosecution forward based on the evidence. Or if there's insufficient evidence or evidence to the contrary, then the suspect would be exonerated, and the whole process would get repeated until the correct suspect is found. The person actually responsible is who we would like to prosecute, right? So, and unfortunately, there are cold cases where that person is never found, but hopefully the evidence and any witnesses, credible witnesses that is, would be able to bring the true suspect to justice and get justice for the families. Okay, so to wrap up our first unit, we started with safety because safety is important, and we want to make sure that we underscore the importance of safety by having a discussion of safety, which may seem a little out of place in a fully online lecture and lab course, but again, since some of you may be going on in science, it's good for all of us to have an understanding of why safety is so important in the natural sciences and what the basic safety procedures and safety features are in a scientific laboratory. The nature of science. Science is a process as much as a product. As I said before, science is a verb. You do science by approaching the world in a scientific manner. And so we talked about the scientific method as a very active idea, and the traditional scientific methods sort of presented as this prescribed deal where you come up with a problem, a question that you're going to explore. Sometimes, as I mentioned with the example of conducting polymers, it's a lot more fluid than that. It's just, this is neat, I want to know more about it, and that study of that particular substance could lead to a breakthrough in the field. Finally, in forensic science, things are a little different because the area of study is something that's already happened. It's a past event, and we're trying to piece together all of the evidence available to determine how that event occurred, and if that event involved criminal activity or civil illegal activity, then we want to make sure that to the extent possible that activity is prosecuted to bring justice and punishment to the guilty and justice to the families and that sort of idea. So hopefully you've enjoyed this first lecture, and we'll go on and see you again for Unit 2. Have a good night or a day, whatever time you might be listening to this, everyone. Bye-bye.